Okay, so here we are on campus. We're going to take a look at a simple series parallel combination circuit. And the first one that we're going to deal with is the following. So hopefully you can see that. You got a battery, or a DC source in this case, that is attached to a resistor and then a parallel combination of resistors, okay, like this. And hopefully I'm speaking at an appropriate volume. I'll try to keep it right up. And we'll see how it turns out. Might need to retake it. So we have 100 ohms of resistance in that resistor. We have 220 ohms in this resistor and 100 ohms in this resistor over here. And the things that we're going to look at are the voltage drops across each one of those resistors. Okay? So here we're going to take a look at the theory, and then we'll take a look at the experimental values that we get when we build this out on a breadboard. First things first, we know that the battery and the resistor are in series with one another, because whatever current happens to come out or be flowing through this circuit, the total current, must pass from positive towards negative, okay? And there's no other path for it to go through except to go through that 100 ohm resistor, this one, right there. And then, and only then, does it get to this junction. The green marker is not behaving itself well here, but hopefully vivid enough for you to see it in the video. And then it's going to split off into two pieces, okay? One's going to go through that branch, the other's going to go through this branch, and we know from our studies of parallel circuits that those currents are going to be in inverse proportion to the resistances in each one of those branches, all right? And then both of those currents will flow back together at this juncture and return to the battery as the total current in the circuit, as there are no other options for the current to take once they flow back together at this junction. All right, return to the negative, and it continues flowing continuously, okay? Now, if we wanted to know what the voltage drops were across each one of these resistors, we want to do a combination of Ohm's law, our rules for combining series and parallel resistances, and also the loop rule, otherwise known as Kirchhoff's voltage law to the engineering folks, okay? So what do? Well, we know that in this case that we're going to apply 3 volts to this circuit. And that means that we know the total voltage drop across all of these resistors in combination. Pardon me. And if you want to know what the voltage drops are across each one of these, well, first you need to know the voltage drop across this first series resistor. We know it experiences the total current. We know what its resistance is, so we can use Ohm's law once we know the total current in the circuit to figure out what the voltage drop is here. Once we know what the voltage drop is across this resistance, then we know that the rest of the voltage must drop over both of these resistors. They are in parallel, so they must both drop that same remaining portion of the total of 3 volts being applied to the circuit. So what does that process look like? Okay? So first let me label these, number 1, number 2, and number 3, just so we have some subscripts to label all of our various quantities. If we want to know let me not go up there because I think that's off frame. If we want to know what the voltage drop is across resistor number 1, then we need the total current, in other words, the current passing through it, and we need to know its resistance. We know just one of those things. We need to find the total current. Total current, we know, is going to be related to the total voltage being applied, which we know, 3 volts, and the total resistance of the circuit. Okay? To find the total resistance of the circuit, well, we've got one 100 ohm resistor in series, and then we've got two resistors that are in parallel with each other. But we can use the inverse rule for combining resistances in parallel to find what that equivalent resistance is. You'll find, if you go through the calculation, that it is 68 3/4 ohms, which means that the total resistance is 168.75 ohms. All right then, so we can take this, bring it over here, plug it in for total resistance to find the total current. The total current with just mild amounts of rounding is that many amps. Okay, probably should put amps on there. That's 3 divided by 168.75, so it being in the hundredths of amps makes sense, okay? A smaller number over a larger number. And then we can take that total current and we can substitute it back in here, okay? And when you do that and you multiply it by 100 ohms, which is the value of R1, you get a voltage drop that is equal to 1.78 volts. Okay, so we know one of the voltage drops across one of the resistors, and now all we need to do is find the voltage drops across the other resistors. Now I'm moving a little farther away from the camera, so I'll try to draw a little bit bigger, but there's not much more to do here. We know from the loop rule that 3 volts has to equal the voltage drop across that first one, and then it has to equal the combined voltage drop across those 2 and 3. I'm writing them as one term because they are in parallel, so the voltage difference from here to there is equal to the voltage difference from there to there. And so if we find this voltage drop, then we know what the individual voltage drops are across each resistor in parallel. Which is nice. Now we already know this first term, we just calculated it. And then we can use V23 is equal to 3 minus 1.78, okay, which gives us 1.22 if I'm not mistaken. Even if you keep some extra digits of precision, it should come out to that when you round to 3. And that is going to be the voltage drop across number 2 and the voltage drop across number 3. So, in the next video, we'll take a look at how to implement this circuit on a breadboard, take this circuit diagram and turn it into something that is a bit more tangible. And we will measure these voltage drops to confirm that the loop rule, Ohm's law, and our rule for combining resistances are not steering us incorrectly. Okay, so I'll see you then soon.